So let's start with the ninth example. In this one we have the first order differential equation dy dx equals 2x. So what we are now claiming about this is that this function f0 from R to R defined by this rule f0 of x equals x square is an explicit solution of this differential equation. There is a reason for calling it f suffix 0. The significance of this 0 will be revealed soon. Okay, so we have to verify whether this really is an explicit solution. Now you can just say that I can immediately see that it is, because you just differentiate the function, you get 2x. So the derivative equals 2x. True, it's an explicit solution. But recall that we have seen the definition, the actual definition of implicit and explicit solution. So let us go about it a bit more rigorously. It may seem like an unnecessary adherence to definition, but do not forget that we are doing mathematics and we have to be absolutely careful about everything. If you keep on using things carelessly, you may forget many fine aspects of a definition. This is what usually happens. Instead, ideally what should happen is that for the first 100 or 1000 times, you have to follow each and everything in the definition carefully, writing everything down. Then only after much practice, when you have become quite familiar with the things, can you afford to be a little sketchy. And that is why let us first express this equation in the form we have seen in that definition, the definition of a solution. So the equation can be expressed like this. We have only dy dx here because the equation is a first order equation. So we do not have the higher order derivatives. Where what is f? F is a function from R3 to R. R3 to R because there are 3 inputs. And what is the function? The function at a 3 vector like this can be taken as z minus 2x, the third component minus twice the first component. So this is a well-defined legitimate function. So what does it mean to say that this is an explicit solution of this equation? It means 3 things. Recall the definition. First of all, let us choose any element x in the domain of the function f0, which is R in this case. So if we were recalling the definition, how did we define an explicit solution? An explicit solution is some function f from I into R, where I is some interval in R. In this case, that interval is R itself. That means this. R itself is also this unbounded interval. Okay, now what are the 3 things we have to verify about this function? The first thing is that the function should have a first derivative. That means it should be differentiable at x. Is that true? Yes. And what is that first derivative? You already know from calculus that this is 2x. Okay. That is the first thing. What is the second thing? The second thing is that for such an input x, you consider this 3 vector x f0 prime of x. You consider this 3 vector, which in our case is x x square 2x. Does it belong to the domain of f? Yes, because the domain in this case is the entire R3. So this belongs to R3. That is the second thing. And what is the third thing? The third thing is that if you take this vector and you put it here in the function f, you should get 0, real number 0. Are you getting? Let's see. So that means this is x, x square, 2x. What does f do? F takes the third component of the input vector, and from that it subtracts twice the first component. So yes, we are actually getting 0. And whatever we did here, we did that for any x in R. That means this is true for all x in R, that means for all x in I. Yes. Now we can say without any doubt that this is really an explicit solution of this differential equation. Similarly, if one goes and considers these other functions, fc from R to R defined by fc of x equal to x square plus c, where what is c? C is any real number. Any real number means once you choose a particular c, you then do not change that c. So c has the status of some arbitrary constant. So once you choose that c, for example here we have c equal to 0, then that 0 remains 0, and then that does not change with x. You can see that if you substitute c equal to 0, you recover the function f0. That means this is a member of this collection of functions. One can go through a process like this and show that for each c, this is an explicit solution of this differential equation. And that is why we are getting in this form an infinite family of solutions. Now, in this infinite family, the constant c is sometimes called an arbitrary constant or a parameter, and with that term defined, this family itself is called a one parameter family of solutions. We stress on the number 1 because you will see later that in some situations you may have more than one parameter. So this is called a one parameter family of solutions of the above differential equation. Usually we do not write like this. Usually we write the family like this. But of course the meaning is same. Now at this stage we cannot show something, although it's true, namely the fact that these are all the solutions of this differential equation. Just now we said that each member in this family, that is, you fix some C, you get one member, just like that F0, there will be F1, F2, in fact F minus 1, F square root of 2, all possible kinds of members are here. For each one of them, you can verify, like we verified for the F0 case, that the corresponding function is an explicit solution. That can be done. However, for some reason, at this stage, we cannot show that these are the only solutions, but it's a fact. Okay. The above family includes all solutions of the above DE, differential equation, that means this one. Okay. Now, from this discussion, one should not, of course, however, draw the conclusion that for any first order differential equation like this, there will be a one parameter family always of solutions which has all the solutions. That's generally not the case. In general, some equations like this, which are first order ODEs, ordinary differential equations, do not have any solutions. That's also possible. We will come across such examples in the exercises. Additionally, there are some first order equations which have one parameter families of solutions, but besides that family, there are some extra solutions, one or more extra solutions where the functions do not look like any member of that one parameter family. Some extra solutions are there. Such examples also we will see in the exercises. Okay, so this is just one case where it happens that the equation has only these solutions. All right. Now, you may notice one thing. You have a differential equation and you have its solutions. Let's take it for granted for now that these are the only solutions of the differential equation. So, these are precisely all the solutions. Now, we can look at this situation from another point of view. This equation is telling us or defining, let me write it in words. dy dx equal to 2x defines the functions or the family of functions in what sense are we using the word defines? That's because every member of this family satisfies this equation. Conversely, any solution of this equation is included here. So, in that sense, once you know this, you know all of this. Okay, now you may ask, okay, fine, we can look at it this way, that a differential equation is defining a family of functions, namely its solutions. But how do we, in what sense is this defining this? In the sense that, say, from the theory of differential equations, we haven't really seen the theory yet, right? We have just seen one or two definitions. So, there is an entire theory of differential equations, just like you have theories of ordinary linear equations, systems of linear equations. Say a system of linear equations is given to you, which is something you consider in linear algebra. There are conditions or there are tests that let you say whether a given system of equations has or does not have solutions. So just like that, from the theory of differential equations, a particular type of equation, by looking at the equation and seeing some conditions, if it satisfies those conditions, then you know that there are solutions. You don't really know what the solutions are, but you at least know their existence. Then you can say that your differential equation defines a class of functions. And then later, if you apply some method or something to actually find the members of that family, namely all the solutions, then those functions that are found as solutions to the differential equation, they are being defined by the differential equation. In fact, this is how some familiar functions which are familiar to us right now, for example, exponential function, logarithmic function, and in fact trigonometric functions, hypergeometric functions, Bessel functions, these things arose for the first time as solutions of differential equations. That is, these equations are their source. Okay, so that's why differential equations become analytically also important, because they can be looked at as means of defining new classes of functions. And that's actually a very powerful point of view. We will see more about this when we study differential equations and when really new functions arise in this way. We are already so familiar with exponential, logarithmic function, trigonometric functions that we may not really appreciate this point of view right now itself. But when we see other higher transcendental functions, then we will appreciate, oh, this is how they are arising from differential equations. Okay, so that is one way of looking at differential equations. And now, we are next going to see the geometric significance of differential equations. Say you have a first order ordinary differential equation which looks like this. dy dx equals f of x comma y, where f is some function of this two variables x and y. So in general, f looks like this. F is a function from some set D into R, where D is a subset of R2, obviously because this is how an input of F looks. Okay, so D has to be a subset of R2. What subset? That will depend on the function F itself. Alright, now what is this equation telling us geometrically? Say we know that this equation has a one parameter family of solutions, something like this. Where C is the parameter or that arbitrary constant of this family. Just like this one has this one parameter family of solutions, say this one also has this one parameter family of solutions. Capital F is something, some function. Okay. Now let me just pick some member of this family by choosing a particular value of C. And to express things more simply, let me just call that member G, y equal to G of x. Actually, this G of x is f of x comma C for some particular C that we understand. Alright. Now, what does it mean to say that, again we are going back to that thing. So, we are saying that this is a one parameter family of solutions, which means, by looking at the members of this family, we can see that each one is an explicit solution. So this is also an explicit solution. What does it mean? It means that g is a real valued function on some interval I in R. Alright. Now what are the conditions g has to satisfy? First of all, g has to be differentiable. Let me just take any point x in I. The first condition, g has to be differentiable at that x. That is, this should exist. Okay, since this is an explicit solution, this exists. What is the second condition? The second condition is that, well, in order to talk about the second condition, say this is what happens when we are not really rigorous. No, we suddenly become confused. Actually, this is not how the general differential equation looks. Ideally, it looks like that, no, which uses that capital F. Otherwise, things will become a little confusing if we just simply work with this. Instead, just like what we did with that equation, dy dx equals 2x, let us also express this first in that form. F, yeah, F, here you may confuse this F with this F. So let me give it a different name. Say G. Dy dx equals 0. Where what is G? G will be a function, yeah, but now be careful. There we had a specific equation where this side was 2x. Now, however, we don't really know. It all depends on this function f. So let me just write the thing and then you will realize that this is correct. I am just considering this as the domain of G. Shall I run into any kind of trouble? We will see, okay. So what is the definition of G? Yeah. Well, the definition is not really that complicated. It is just, you can consider this. Does it make sense? Is capital G well defined? Let us first see that. Suppose I am taking an input here. Okay. What does it mean? It means that this this vector with two components belongs to D. Alright. But D is the domain of F. So if I evaluate small f at this vector, it makes sense. And it's going to be a real number. And from that, if I subtract this arbitrary real number z, I'm also going to again get a real number, a unique real number in fact. So yes, G is well defined. Okay. Yeah, now we can verify in what sense this is an explicit solution. So G prime of x exists. What else? For this x, if you then consider this 3 vector, first of all, this 3 vector should belong to the domain of G. Now the third component, we do not have any problem with the third component because it can be any real number. But what about the first component? The first 2 components. The first 2 components should make a 2 vector which has to belong to D. Does it really belong to D? Yes, because we have already considered that this is really an explicit solution. And then based on that assumption, we are writing these things. And what is the third thing? The third thing, of course, is that if you just write x, y, dy, dx in place of this function, then you should get 0. Since this is an explicit solution, So what will you get here? F of x comma g of x minus g prime of x. Is that 0? Yes, because this satisfies this differential equation. That is why. But what do all these things mean geometrically? That's what we want to see here, right? So now you look at this figure. So here what is happening is that we have drawn the graph of this function here. Keep in mind that this function is defined only on I, which is an interval. To keep things simple, I have taken I to be a bounded interval. I may be unbounded also. I may be the entire R also. So this is our I. These are the endpoints of I. So depending on what the actual function g is, the graph will be something like this, but it will be bounded between these two vertical lines which pass through the endpoints of I. So that is the graph. That's the graph of y equal to g of x. Alright. And then what we did, we chose one point x inside this I. Okay. And we have found the derivative of g at x. Now you know from calculus that this derivative at x is the slope of the tangent to the graph of the function, where at that point where the x coordinate is x, your chosen point. So what the differential equation is telling us is that it is directly telling us that slope, what the slope of the graph will be at any given point. So what is that given point here? That given point here is x comma g of x. We do not need to mention g of x, but if you write the coordinates of that point where we have drawn the tangent, the coordinates are x, g of x. So at all the possible points on the graph of this equation or this function, the differential equation tells you what the slope should be. So in that sense, the differential equation is telling you how the tangent at every point is tilted, what the slope of the tangent is. So at once the differential equation gives you information about possible slopes along the graph. Graph of what? Graph of this solution of the differential equation. Okay, so this is an information about slopes. That is the geometric significance of differential equations. Means this first order differential equation. If you go to higher derivatives, then the geometric meaning will change. For example, if you consider second derivative, instead of simply slope, you will have things like radius of curvature. So those type of things will be there. But more or less, this is the geometric significance of differential equations, that they tell you what the slope at any point on the graph of the solution will be. But I should not say the solution, because this is just one member of this family of solutions. There will be other members also. So is the differential equation telling us about slopes of tangents to those members as well? Yes. Simultaneously it is telling us. So in a sense, you see, when you know how the tangent is tilted, at that point you know in which direction the solution graph is going. It is instantaneous, we understand that, but that's what the tangent tells us. It's something like this. No, say you have tied one piece of rock or something heavy by a string, and you are rotating it like this. Now, as your speed increases, the tension in the string increases. So when it reaches breaking point, what happens to the stone or ball, whatever it is? It flies off tangentially. So although it was rotating in a circular motion around you because it was bound by that string, but at each instant of time its tendency is to fly away tangentially. So at any instant, that is the direction in which it wants to go if it is not constrained. That is the tendency of the tangent. The tangent gives you the instantaneous direction in which the curve wants to go at that point, but the next moment it just changes. So there also the tendency itself changes. So by telling us about what the slopes will be at every point, essentially the differential equation is telling us about how the curve will be, and that too not one curve, all the curves which are its solutions. So that's the geometric information that the equation gives us. And to better understand this in a particular situation, let's see the next example. Oh, and one more thing I forgot. You see, you may notice that I have drawn D here, this region. So you just recall that D is a subset of R2. The D I have drawn here has some properties. As a subset of R2, it looks connected. Also, it is bounded. That's not necessary. That's what I want to say. That's not necessary. D may be unbounded, D may be disconnected, D may look very bad, D may not look like a region like this, it may be a collection of points, anything can happen. But the graph of the equation, the curve that we will get, has to lie inside D. Okay, so you notice that also. Alright, so let's now see the next example. The next example actually is again that equation which we saw in this example. But now we are going to look at it with the geometric interpretation. So this is our example 10. 110 actually. So you again consider our first order equation. Okay, and we already know, means we have agreed to the fact that these are all the solutions to our differential equation. For every real number C, this is a solution, and these are all the solutions. So this is the one parameter family of solutions of this equation which has all the solutions. Now, you of course know how the graphs of these things look. They are these parabolas. In fact, to declutter this part of the board, let me get rid of these things. We have already understood these parts. So let us now simply look at this graph. If you take C equal to 0, you get the parabola y equals x square, so which is this, because it passes through the origin. I know the drawing is quite bad because these things don't really look like parabolas, but you get the point. Okay, so all these parabolas will have the y-axis as their axis, and their vertices will be at different locations depending on what C is. If C is 0, then this is the parabola and its vertex coincides with it is the origin. If C is positive, say y equals x square plus 1, then say this is the vertex. So that is the graph of this. Similarly, for some negative value of C, you get this parabola. So this is how all the parabolas will appear. You can understand that if one really imagines the entire family, then the plane itself will be completely covered by everything. So we are only looking at 3 members of this family. Alright. Now, what have we just now discussed about the geometric meaning of this, the thing that this differential equation tells us geometrically is that you take any point, okay, say I take this x. Now, corresponding to this x, there are points on each member of the family. These points, this point, this point, this point, and the other points there will be on the other members, which are also, we are not showing them, but they are there. At all these points, the slope is 2x. The slope of these many tangents, all of them will be exactly the same. That means these tangents will be parallel to each other. At that instant of the input value x, the tendencies of all these graphs is to go in precisely one direction, namely in the direction of that line which is tilted with slope 2x. Okay. So that is the geometric significance. And there are some terms, I forgot to tell you about that. There are some names that have been given to these members. Say you have a 1 parameter family like this of solutions of some differential equation, then you can draw graphs of those functions of those solutions. Those graphs are called integral curves of the differential equation. So for this differential equation, these parabolas are all the integral curves. Okay, so the integral curves are nothing but graphs of solutions of differential equation. That's it. Now, after this discussion, there is a very small discussion about solutions of differential equations themselves. Already we have defined what we mean by a solution, but still there is something to be said about what we are expecting to see next. Are we going to find solutions? If so, in what sense? Shall we be able to find all the solutions if a differential equation is given to us? If not, then what is preventing us? Also, you will see that in many cases, we will have a detailed discussion, although the discussion will be short, but still, you will see that we won't really find exact solutions in almost all cases. We will have to rely on approximate methods, and that will give us approximate solutions, sometimes series solutions, sometimes graphical solutions like this. So these things are there, and once that discussion is over, we will then move on to the actual methods of finding solutions to those differential equations that do have exact solutions which can be found. So for a long time we will learn those methods, and then we will take differential equations which do not have exact solutions, and unfortunately that's in the majority of cases. So there we will have to rely on only approximate solutions. But even with approximate solutions, you will see that we gain so much information that it's more than enough in fact, and the approximations can be improved as much as we can in most cases. So that's just it. Let me end things here itself. And what do we have tomorrow? Oh, trigonometry. Okay. So see you tomorrow with that. Until then, this is me, Lucifer from A Mathematical Room. Have a nice day.